Welcome to Electronic Materials. This video is about Chapter 4. Let me give you a brief overview first before we dive in. So in Chapter 4 we'll basically go from single atoms to solids, and we do that by first going to molecules, and so we will learn that there are anti-bonding and bonding states when we put two atoms together. Now when we look at a whole bunch of atoms like in a solid, then we'll see that these anti-bonding and bonding orbitals turn into bands that have bonding and anti-bonding character. In metals these bands overlap, and that gives us one band that is partially filled with electrons, while in semiconductors and insulators we'll get bands that are separated, and the valence band, which is derived from the bonding orbitals, that is completely full, while the conduction band, which is related to the anti-bonding orbitals, that is completely empty, and because of that we don't have conductivity right away in semiconductors and insulators. Then at the end of the chapter we will look into what happens when we put two materials with different work functions together. That gives us thermocouples. They make it very easy to measure temperatures. And then we will also look into how to extract electrons from metals by heating the metal or by applying a voltage, and that brings us to field emission and how one can make a field emission electron gun. Before I will discuss the hydrogen molecule, let's discuss a few general points to get us in the mood for solids and molecules. The first point I would like to make here is about the symmetry of wave functions. So if you remember the infinite potential well, and when we calculated the solutions of the Schrödinger equation, we got these sine waves. And so here you see that the sine waves alternate between symmetric and anti-symmetric. So why are these wave functions either symmetric or anti-symmetric and nothing in between? Well, the reason for that is that we need to get the same solutions when it comes to the probability densities. So that means when we take the absolute square of these wave functions, if we turn this around 180 degrees. Right, because it shouldn't make a difference whether the electron moves left or it moves right. And so around this point of symmetry within the potential Vx, the wave functions are either symmetric or anti-symmetric, and they are stacked in here in an alternating way, right? We start out with symmetric, then anti-symmetric, and so on. There's another lesson that ports over well to solids that we can learn from the infinite potential well. If you remember, I showed this slide here in chapter 3, and on this slide I discussed what happens when we make A very large. That in effect gave us the solutions for a free electron, the solutions of the Schrödinger equation for a free electron, right? If these potential wells are infinitely away, then the electron doesn't see them anymore, and so it is essentially free. It has no potential acting on it. And what we found here is that when A gets really large, the eigenenergies, they when we look at the formula here, we see that the ground state energy is 0 now, right? So we go from this minimum energy that an electron has to have in an atom to 0 that it can have in a free space. That means it can be at rest, essentially. And the other thing we saw is that the spacing between the eigenenergies got infinitely small also, because here we divide by a, when we call the delta E. And that gave us a continuum of energy states. So in essence, that means that the electron can take on any energy it likes within this continuum of states. And that is very similar what we see in solids, because a solid relative to an atom is huge, and so A is essentially infinite for all practical considerations, and that tells us that in a solid we can expect to get such continua of states too. And that explains why in a metal, for example, we can have a free electron gas, right? These electrons can move around in a chunk of metal very similarly to like being in vacuum. Therefore, what we will see when we go from the atom to molecules to large molecules and then finally to the solid, that we get discretely spaced energy states in the atom, closer together states in small molecules. In large molecules, we get almost a continuum, and in a solid, we get then a band. Okay, let's see how we can make some molecular orbitals. Let's start out with the most easy example we can find, the hydrogen molecule. Here you see the wave function of the 1s orbital of the hydrogen molecule. If you remember from chapter 3, these wave functions are essentially exponential functions that depend on the radius away from the nucleus. And so here we have these two atoms that we want to bond together, make an H2 molecule out of them, and we see here their individual wave functions. At this point you're probably wondering, how do we get the molecular orbitals? Now the formal approach would be to solve the Schrödinger equation for this problem. So you put two electrons into the two Coulomb potentials of those two nuclei and then you solve it. It turns out that this is already pretty difficult because we have four potentials interacting here, the electrons, the nuclei, and one can only solve this numerically. And so a common way to get a first idea how the molecular orbitals might look like is to use the atomic orbitals and make linear combinations out of them. So this is called linear combination of atomic orbitals, in short LCAO. In the case of the hydrogen molecule, there are essentially only two ways to make valid linear combinations between the two atomic orbitals. One is to add them, and the other one is to subtract the wave functions. The reason for that is that we need to find symmetrical or anti-symmetrical solutions that we can get symmetrical probability densities. So here you see what happens. When we add them up, we get a molecular wave function that is significantly positive between the nuclei, and when we subtract them, we get a resulting wave function that is going through zero between the nuclei. Now let's examine the probability density functions that come out of these two linear combinations. The one that came out of the addition, that is the bonding orbital. And it's clear why it's called bonding, because here we have a high probability of the electrons to be in between the two protons, and that has the effect that the positive charges of the protons are shielded from each other by the negative charge that's in between them, while at the same time the negative charges also hold everything together because they attract these positive charges. So this is why this here is the bonding solution, while the other solution is the anti-bonding solution. And it's clear why it's called anti-bonding, because here the probability density is zero or close to zero in between the protons, and that means the electrons will be mainly on the outside, and that doesn't help the bonding process. It's interesting to note that we started out with two atomic orbitals and we ended up with two molecular orbitals. So it seems that in this process we keep the number of electronic states constant. Let's look now at the eigenenergies of these molecular orbitals that we just determined. Here you see the energy curves, the potential energy curves for the two states. The lower curve corresponds to the bonding orbital, while the upper curve corresponds to the anti-bonding orbital. The upper curve reflects the repulsive interaction between the two protons that are not shielded by electrons in between them, so the energy just keeps going up as we reduce the distance between the two nuclei, while the bonding curve down here, that goes through a minimum which defines the bonding radius, and at this minimum the electrons are in between the nuclei and they're just shielded enough from each other while still bonded together that we have an energy minimum. If we reduce the distance further, then the nuclei start seeing each other too much, and then they start repulsing each other, and so this is why the energy goes up again. So the bottom line out of these energy curves is that at the bonding radius we have this split between the bonding and the anti-bonding orbital eigenenergies. Now in the case of the hydrogen molecule, we started out with one single electron per atom, and that means we can put both of these electrons, one spin up, the other spin down, onto the bonding orbital. The consequence is that the energy state of the molecule is lower than the energy state of the individual atoms. That explains why the hydrogen molecule is a stable molecule and why it is difficult to find single hydrogen atoms in nature. Let's see what happens in the case of helium. Helium is very similar to hydrogen, except that it has 2 electrons on the 1s orbital. So if we would like to make a helium-2 molecule and we put 2 helium atoms in contact, again we would get the bonding and anti-bonding orbital, but the difference here is that we have 4 electrons that we need to stack into the molecular states, and that means we have to put 2 up here into the anti-bonding orbital, and that costs energy. And that means that the energy total of this molecule is pretty much neutral, so we release some energy because of these 2 electrons, but we also need some energy because of these 2, and so this is the reason why this molecule is not stable. And that means that in nature one doesn't find helium-2 molecules, but only helium atoms. It's interesting to note that this here nicely confirms what you learned in chapter 1, where we saw that covalent bonding only occurs between partially filled atomic orbitals. In our quest to see what happens in a solid, well, let's try to do this with 3 atoms. So here we put 3 hydrogen atoms together, and again we do the linear combination of atomic orbitals approach. And it turns out if we want symmetrical and anti-symmetric solutions only, there are only 3 ways to do this. So let's focus on the one that corresponds to the bonding state. This is the one where we add up the wave functions between A, B, and C. So this is this one here. And here again we have probability distribution functions that are positive in between the nuclei, in between the protons, and that means that the electrons are most likely to be found in between the nuclei, and that is of course good for the bonding process. So this one here is the bonding orbital that gives us a nice solid energy loss of this system. The next solution is the one where we subtract C from A and multiply B with 0, and that gives us an anti-symmetric solution. And here we have a situation where the electrons are around A and C, but there are no electrons on B, so it's sort of naked. And that means that there is some shielding between the protons, but they also see each other. And so this is not really bonding, but it's also not anti-bonding. So its energy level is in between the anti-bonding and the bonding orbital. Now the third combination, where we do A minus B plus C, that yields again a symmetric solution, and this symmetric solution has probability distributions that are 0 in between the nuclei, and of course that means that the protons here see each other very clearly, and so they have maximum repulsion, and that gives us this really steep energy curve when we reduce the distance between the atoms. If you like, you can draw a parallel to the potential well. If you step a little bit back and you look at the system, you can say, well, these electrons, they are confined to the space around these 3 protons, and this space has a dimension of A, and then these wave functions here out of a sudden start looking a little bit like the first 3 solutions of the infinite potential well, right? This here is a little bit like the single sine wave belly that we had as ground state. Then this here looks a little bit similar to the a full sine wave. That was the second state, and then this here has a little bit of similarity to the third state. Let's stick with this analogy a little further and let's explore what happens if we put a large number of atoms together and make a macroscopic solid. So what happens if we have a potential well that has a macroscopic dimension that spans n atoms? Well, we will get n wave functions, but we will still get a ground state that spans the entire well, and then we work our way up to the most anti-bonding state that will have a wavelength that corresponds to one single atom here. When we look at the eigenenergies, this is what's happening. So we start out with a 2 atoms molecule, we get the bonding and anti-bonding state. And then if we add atoms, we will get more and more states that fill out the space in between the anti-bonding and the bonding orbital. And then if we go to a really large number of atoms, similar to Avogadro's number, if we make a solid, then the spacing will get ever smaller and becomes unnoticeable, and then we can say we have a band here filled with a continuum of energy states. When it comes to putting in the electrons from all these atoms, well, we will again stack them in from the bottom, spin up, spin down in each stage and up to a certain energy level. And this energy level is called the Fermi energy. I also included the core orbitals in this schematic, since most atoms have valence shells that are higher level than 1s. And if there are electrons in core orbitals, for all practical purposes, we can assume that they simply do not participate in the bonding process and that they remain at the same energy level and occupied by the same electrons like in the individual atoms. An interesting question to examine is what happens to the empty orbitals that are on the outside of the valence orbitals in atoms. Since they're even further out, they will of course also overlap with the empty orbitals of neighboring atoms. And so they will also form bands, but of course these bands are empty because there are no electrons in empty orbitals, as the name says. And so what we end up with is a continuous system of energy states from the bands that are derived from the valence orbitals out into the free electron continuum on the energy axis. Let's explore now what is the difference between a metal and a semiconductor or insulator. So far I said that the bands that are derived from the bonding and the anti-bonding orbitals, they overlap and form one continuous band that is partially filled with electrons. Now this is only true for metals. In semiconductors a different thing happens. There is actually a gap between the band that is derived from the bonding states and the bands that are derived from the anti-bonding states. And in semiconductors and insulators, we call these bands now conduction band and valence band. And so there's this energy gap in between them, and that means that the valence band is full with electrons and the conduction band is completely empty. And that fundamentally changes the conductive properties of the material, because in order to accelerate, to take on kinetic energy when you apply a voltage to the material, there need to be empty states nearby on the energy axis that these electrons can go onto to accept this kinetic energy. Now, since there is this energy gap, they cannot accept the energy, and that means that these materials, semiconductors and insulators, are intrinsically pretty non-conductive. They have a very high resistivity that depends essentially on the size of this gap. So there is a gradual transition between semiconductors and insulators that depends on the energy gap. The larger the gap, the less conductive the material becomes. Now you may wonder, why are some materials semiconductors or insulators and others are metals? The main reason for that is simply in the way they bond with each other. which types of orbitals overlap to form the bonds and so forth. So this is just a material property that comes out of the specific character of the atoms that come together and what kind of chemical bonds are forming. Okay, let's have a look what electrons can do in such bands. So let's talk first about metals, or in general in partially filled bands. So when we have electrons in a band that is partially filled, then they can accept pretty much any energy that is thrown at them. So if a photon comes in, the electron can accept the energy and go on a higher energy state within the band. But then, of course, it would simply thermalize, as they say, and go back to the lowest available energy level that's there, while releasing that energy difference as heat. If the photon has a higher energy, then the electron can perhaps make it into the free electron continuum and leave the metal. So this would be the photo effect that I already discussed. When it comes to conductivity, the electrons can of course accept kinetic energy if we apply a voltage to the material. So they simply go on a higher energy state based on how much kinetic energy they accept from the applied potential. So this gives us conductivity. And then of course they can also accept thermal energy, which means that they go on a empty state that is about kT away from where they came from, near the Fermi energy. Let's see now how different the situation is in a semiconductor or insulator material. So in semiconductors and insulators, we have a energy gap between the full valence band and the empty conduction band. The consequence of this is that the electrons in the valence band can only accept energy amounts that exceed the energy gap. So that means that a photon that wants to be absorbed needs to have an energy that is larger than the energy gap. If the photon energy is lower than the energy gap, then the photon simply gets transmitted through the material and does not get absorbed. So the material then becomes translucent to that photon energy or frequency. Let's assume now the photon has an energy larger than the energy gap, then the electron can be excited into the conduction band. The energy difference relative to the bottom of the conduction band, that typically is released as heat, and the electron then occupies a state at the bottom at the conduction band. Now, an electron that's excited into the conduction band leaves behind an empty state in the valence band, and that empty state is positively charged because a negative charge is missing. The existence of these empty states in the valence band enables the electron to recombine with one of those under release of a photon that has the energy corresponding to the band gap. So we get photo emission from such an electron that goes back down into the valence band. When it comes to conductivity, the main difference between semiconductors, insulators, and metals is that we need thermal excitation of some electrons into the conduction band before we can have any conductivity at all, because a full band cannot conduct any current because there are no empty states here nearby in the energy gap that the electrons could go onto when they accept kinetic energy from the applied potential. So a semiconductor only becomes conductive when there is some thermal excitation of electrons into the conduction band. At temperature 0, a semiconductor becomes a full insulator that cannot conduct any current. So it's obvious that the higher the temperature, the more electrons we will have up here, and the more conductive the semiconductor is becoming. Of course, another way to get more electrons into the conduction band is to have a narrower gap. So if the energy difference between conduction band and valence band is smaller, then thermal excitation will also be able to bring more electrons into the conduction band. So one can generally say that a semiconductor with a smaller band gap will be more conductive at a given temperature than a semiconductor with a larger band gap. And the insulators, they're just by extension semiconductors with really large band gaps, so that the thermal excitation is just very, very little. And so we have only very few electrons in the conduction band in an insulator, and that means that essentially no current can be conducted. Another big difference to metals when it comes to conductivity is that in a semiconductor we don't only have an electron current, we also have a hole current, because those positive charges, those holes that are left behind in the valence band, they can also act as charge carriers and move in the opposite direction of the electrons and conduct their own share of the current. So in a semiconductor we always have a sum between an electron current and a hole current. Now it's time to have a look at an example, a real-life example. Silicon. Silicon is probably the most used semiconductor material. It is the basis for microprocessors, memory devices, and most digital analog and analog integrated circuits, as well as many micro-electromechanical systems. The valence shell of silicon is composed of 3s and 3p orbitals that are filled with 4 electrons. Now, in order to create that tetrahedral bonding scheme that you find in a FCC lattice, these 4 orbitals have to combine into hybrid orbitals that are called sp3 orbitals, and each of them then carries one of these electrons. So they are degenerate, they have all the same energy, and so silicon can bond to another silicon at each of those corners of the tetrahedron. Now when silicon atoms bond, they of course also form bonding and anti-bonding orbitals. And since we only have one electron in each of these sp3 hybrid orbitals, we can put both electrons that participate in such a bond into the bonding orbital. Now when we put many silicon atoms together, we get a valence band and conduction band. And the conduction band is separated from the valence band by an energy gap that is 1.1 electron volt in size. That means that silicon absorbs all visible light, because visible light starts at 1.6 electron volts for red and tops out at about 3.1 electron volt for violet. That's when the ultraviolet range starts up here. The valence band is of course full, and the conduction band is empty. Before we go on and discuss the distribution of energy states in bands, we need to discuss one more item that is different in the quantum mechanical treatment of solids compared to the Drude model that we encountered in chapter 2, and this item is the electron effective mass. If we accelerate an electron in vacuum, then the acceleration is simply given by Newton's second law. Now, if we put the electron inside a crystal lattice, of course then there are many interactions with that crystal lattice, and so we can expect that the acceleration with a given external force will be different for that electron. You can probably imagine that it is rather difficult to exactly calculate the influence of the crystal lattice on the electron motion. And so there is a more practical approach that is sufficient for many applications to take into account how the crystal lattice interacts with the electron. And this approach is shown here. We simply say that the influence of the crystal lattice can be summed up into an internal force that acts in addition to the external force on the electron and determines the acceleration. And then we can say, well, this can just be expressed as a constant with which we multiply the electron mass. And so we have essentially, depending on what type of crystal the electron is in, we have an electron that is a little bit heavier or a little bit lighter. And then if we calculate the acceleration with the external force, we still get the right number. And so here you see a table how the effective mass varies relative to the regular electron mass. And so you see that there are quite some differences. Silver, for example, has an effective mass that is identical with the regular electron mass. But if you look at bismuth, for example, it's about a factor 100 different. When we look at semiconductors, then of course we need to keep in mind that semiconductors have electrons and holes as charge carriers that participate in electrical currents. And so here, consequentially, we have two effective masses, one for the electrons and one for the holes. And you can see in the example of gallium arsenide, there can be quite some differences between the electron and hole effective masses. So in a flashback to chapter 2, to the Rudy model, if you wanted to calculate the mobility, you would really have to use the effective electron mass here instead of the regular electron mass. So far, when I talked about bands, I always just drew a box and I told you that there is a continuum of states in there, but I never really discussed how these states might actually distribute across this band. And so it turns out that this distribution is not homogeneous, but we have differences between the band edges and the center of the band in how close these states are stacking up inside a band. And so here I want to give you first an intuitive approach to determine how these energy states might be distributed within a band before we calculate it at the example of the infinite potential well. Let's consider a string of atoms that form a solid that react with each other. And so you know now that atoms that are close together, they form bonding and anti-bonding states, and these two states have a sizable energy gap in between them. Now, if the atoms are further apart from each other, you also know from these energy curves that you saw earlier that the bonding and anti-bonding orbitals will be closer together, right? If we have a larger distance between them, then the anti-bonding would be up here and the bonding would be down here. So we get states that are much closer together around the center of this band here. And so if you now consider that most atoms interact with most other atoms over a large distance, while only each of them sees its direct neighbors directly in a close distance, it is obvious that we will get many more states in the center here than at the outside of this band. And so in general, one has a distribution in these bands where the density of states is larger at the center compared to the fringes. And that is shown here as a density of states curve that has its maximum in the center. Since we now have a density of states function g of e, if we want to determine how many states do we have up to a certain energy level e prime, then we need to calculate the integral from 0 to e prime over that density of states function. And then we can calculate the total number of states per unit volume SV. I just promised you that we would calculate the density of states distribution based on the infinite potential well. So here we go. So the approach for this calculation is that first we need to determine the number of energy states up to this energy E prime. So that means we need to find a way to calculate this integral. And then once we have the integral, we differentiate it in energy and get g of e. Let's remember now that the formula for the eigenenergies of the infinite potential well is this here, and this assumes that the infinite potential well is a cube with a equals b equals c, and so we can just call it L for the length of the size of the cube. And these energies depend on the three quantum numbers that are added up in their squares. So if we plot the eigenenergies in the n space, as I call it, so we have this coordinate system where on each axis we have one of the quantum numbers. So each cube that we can define with one combination of these three quantum numbers corresponds to one of the eigenenergies. Since this is a cube, all combinations of n1, n2, and n3 that yield the same radius here have the same energy. That means that all cubes that are intersected by this sphere that is defined by the radius n prime have the energy E prime. Therefore, if we want to know the number of states that are below E prime, all we have to do is calculate the volume of this sphere and take 1/8 of it, because we have only positive quantum numbers. And with this it gets pretty easy. All we have to do is to use the formula for the volume of a sphere and plug in n prime and divide by 8, because we only want the positive part of this sphere. And so we get 1/6 pi times n prime cubed. And if we calculate that for the example shown in this figure, here n prime seems to be 9, then we can calculate that inside this octant shown in the figure we have 381 cubes or states that are below that energy E prime. At this point we're not quite done yet, because each of the states can be occupied by 2 electrons, one spin up, one spin down, and that's why we need to multiply this by 2, and so we end up with this here. At this point we know the number of electron states below E prime, but we only know it dependent on n prime. And if we want to differentiate this to get the density of states function g of E, we need to express this here in energies. So we can do that by replacing n prime with E prime using the formula for the eigenenergies. And when we do that, we get this expression here that gives us the total number of states below E prime. But this is not a density yet, because we have the volume of the cube in here, so we need to divide this here by the volume of the cube, and we finally end up with this here as number of states per volume below energy E prime. The final step is to differentiate this expression in the energy, and that yields finally g of E, which is a constant multiplied with the square root of the energy. And so if we plot that here starting out at the bottom of the energy band, we get here this square root function. So this seems to match the prediction of our intuitive approach at the beginning fairly well. We have a low density of states at the band edge, and we have a high density of states in the center. Now this model doesn't seem to hold for the upper half of the band, where our intuitive approach suggested that the density of states should go back to 0 again. But this is not so important, because most of the action in a semiconductor is at the bottom of the conduction band, and that's why for the rest of the course we can live with this approximation. Now that we understand how the density of states is distributed across a band, the remaining task is to put in the electrons. Since we have a large number of electrons, we need to do this with a statistical distribution function. And for temperature 0, such a function is easy to come up with, because at temperature 0 we have this clear division between full states and empty states. So we can say up here the probability to find an electron on a state is 0, and down here it is 1. And so that function would look like this here. So it would start here at 0 and then jump up at the Fermi energy to 1. It gets a little bit more complicated when the temperature is not 0, when the electrons have some thermal energy, because that means that some electrons close to the Fermi energy will jump up on higher states and occupy them. And at the same time, of course, they will vacate states down here. So there are some empty states below the Fermi level. That means that this statistical function will blur around the Fermi energy. Now this behavior can be described with the Fermi Dirac function that you see here. Note that in the exponential function there is the difference between the energy and the Fermi energy. So this is symmetrical around the Fermi energy. And it has to be symmetrical because every time an electron jumps up, it vacates a state down here. So there needs to be the same number of empty states down here as we have full ones up here. And that's why this function needs to be symmetrical around the Fermi energy. If the temperature goes to 0, then this Fermi-Dirac function turns into this step function. It's also interesting to note that when you go a little bit away from the Fermi energy, a few kT up, then this Fermi-Dirac function can be approximated with a simple exponential function. That's very similar to what we did for the Boltzmann distribution at higher temperatures. For the fun of it, I went over to Wolfram Alpha, really nice website if you want to do a quick plot of a function or some other easy math. And what you see here is I put in the Fermi-Dirac function and I told it to plot it for temperatures from 0.1 Kelvin to 1000. So this is the temperature axis. And on the x-axis, we are plus minus 0.5 electron volts around the Fermi energy. So at 0, that's the Fermi energy. That's actually an energy scale that is often used in literature because the Fermi edge is an easy reference point in many measurements that one can do on semiconductors and other materials. On the z-axis, that's the probability, so it goes from 0 to 1. And so you see here that at the 0.1 Kelvin temperature, we have almost a step function. Of course, you cannot evaluate the Fermi-Dirac function at temperature 0 because we would have to divide by 0, which is not possible. So we can only go close to 0, but you see it's pretty much a step function here. And then as we go to high temperatures, to 1000 Kelvin, the Fermi function smoothens out very nicely here. And you also see that it is really symmetrical around the Fermi energy for all these temperatures. It's interesting to note that the symmetry around the Fermi energy is used to define the Fermi energy itself, because the Fermi energy is defined to be at the point where the probability to find an electron is just 0.5. And now we're ready to put it all together. So we understand now how the density of states is distributed across the band. We know how to put the electrons in with the Fermi-Dirac function. And if we multiply these two functions, now we get a picture of how the electrons stack into the band. If we multiply the density of states with the Fermi-Dirac function, then we get the number of electrons per unit energy and unit volume. That's the blue curve here. And if we take the integral over this curve starting at the bottom of the band at 0 and we integrate to the top of the band, then we get the total number of electrons per volume that are in this band. Let's have some fun with this integral and calculate the Fermi energy within the conduction band of a metal. So here we have that electron density per volume, and if we plug in the expressions that we found earlier for the density of states and the Fermi-Dirac function, we get this here. And if one evaluates this integral for temperature 0, which makes this much simpler because this here goes to 0, then we can calculate the Fermi energy at 0 Kelvin, which is this expression. Let's use this formula and calculate the Fermi energy for copper. Copper has a electron density of 8.5 times 10 to the 28th per cubic meter, and with this now we can calculate the Fermi energy at temperature 0. So we look up Planck's number, plug it in here, we divide by 8 times the mass of an electron, and here we multiply 3 with that electron density and divide by pi. And if we evaluate this, we get 1.12 times 10 to the minus 18 joule. Right? If you look at the units here, we get joule square times second square divided by kilogram meter squared, and this here is just 1 divided by joule, and so 1 joule divides here out, and so we're left with the proper energy unit. Now, if we want to convert this into electron volt, then it's useful to convert the joules into Coulomb volts. Then once you have the Coulomb volts, you can just expand this here by electron charge divided by electron charge, but the upper electron charge here you just leave as the symbol E for the elementary charge, and then you divide the 1.12 times 10 to the minus 18 with the 1.602 times 10 to the minus 19 Coulomb, and the coulombs divide out, and so we're left with 7.05 electron volts. So in electron volts, this here is the Fermi energy relative to the bottom of the band. It's interesting to look at the velocity of the electrons that are in this conduction band. One can show that the average kinetic energy of the electrons is 3 divided by 5 times the Fermi energy at 0 Kelvin. And if you evaluate this and solve it for the velocity with the energy that we just calculated here, we arrive at 1.21 times 10 to the 6 meter per second. It's interesting to consider this in relation to a typical drift velocity in a circuit, which is around 10 to the third meters per second, 1,000 meters per second. So this is several magnitudes faster than that drift velocity. That means that when you apply a voltage to a circuit and you get a current, the electrons drift in that direction of the current at a much, much slower pace than they use in their random walk throughout the circuit. But of course, this random walk doesn't contribute to the current that you're measuring. It's also interesting to look at this in relation to the speed of light, which is 3 times 10 to the 8 meters per second. So realize that this is only 2 magnitudes slower than the speed of light. On the previous slide, we calculated the Fermi energy relative to the bottom of the band. Now it's very interesting to also consider its position relative to the vacuum level. If you remember, this is the work function of a material, and that defines the amount of energy that an electron would need to be able to leave the material and become a free electron in vacuum and be able to move away. So it's really interesting to consider what will happen if we put two materials with different work functions into contact. So the example here is platinum as high work function material. Platinum has a work function of 5.36 electron volts, and molybdenum on the other side, which has a work function of 4.2 electron volts. So what will happen when we slap these two materials together and we have electrons at a high Fermi energy facing empty states on the other side, where the electrons are only filled in up to a lower Fermi energy? Obviously, once they are in contact, the electrons on the molybdenum side will feel compelled to move over on the platinum side because they can lower their energy with that, and we know that nature likes to do that. But of course, the price for that is that positive charges are left behind in the molybdenum because some electrons are missing here now. And remember, matter is usually neutral, so we have the same number of electrons and protons. So when electrons leave, we will have some protons that are not compensated anymore. So we get a positive charge build up inside the molybdenum, while on the other side, of course, we get negative charges because here now we have too many electrons. So the moment we make the contact, these materials are lined up at the vacuum level, but then because of this charge built up on both sides, we get something akin to a capacitor at the interface. These two charges, they attract each other, so they will all hang out here close to the interface between the materials. And that here is essentially an electrical dipole that gives rise to a contact potential at the interface. And that contact potential is responsible for this shift between the vacuum levels. And that essentially causes the Fermi levels to line up across the entire structure, and at that point that charge transfer stops. You need to imagine this as a gradual process where we put them together. then charges go over to the platinum side, and at that moment the two vacuum levels start drifting apart until they reach this point, where the contact potential corresponds to the difference of the work functions between the two materials, which is 1.16 electron volts in this case. It's interesting to note that the Fermi energies themselves within the materials do not change significantly because of this charge transfer, because the number of electrons that cross the interface during this process is much smaller than the total number of electrons that are in the bands. I just said we get this contact potential between the two materials when they are in contact. So one could wonder, well, why don't we use this voltage here as a battery to drive an electrical current through a load, which would be this voltmeter here. So if we connect this platinum piece here with two molybdenum wires, right, and connect them here to this voltmeter, well, unfortunately, because the Fermi level is constant throughout the entire structure, the whole thing is at thermodynamical equilibrium, and that means that there is no energy difference between electrons on this side and electrons on this side. And of course that would mean that no current is flowing and that we don't get any voltage on this voltmeter. What we really need is a difference between Fermi levels on either side of that circuit. Only if we have a difference between the Fermi levels, we have electrons with high energy on one side and empty states on the other side where they can go to, and then we can drive a current throughout a circuit. So how can we generate a Fermi level difference in such a structure? The answer to this question is the Seebeck effect. With the Seebeck effect, we can create a Fermi energy difference by establishing a temperature gradient across the material, and that causes a voltage difference. How does this work? Well, on the hot side of the material, we get a Fermi Dirac function that is spread out, while on the cold side, it's more close to being a step function. That means that on the hot side we have electrons that can move faster than the electrons on the cold side. The consequence of this is that there is an electron diffusion over to the cold side, which creates a negative charge on this end. And of course, because protons are left lonely behind on this side, we get a positive charge built up on this end. The result of this charge exchange is that a voltage builds up across the material. And this voltage we can actually use to drive a load, or we can measure it on a voltmeter. So this build-up of a voltage across a material due to a temperature gradient is called the Seebeck effect. Each material has a Seebeck coefficient, which is a material's property, and the Seebeck coefficient essentially tells you how much voltage is produced depending on a certain temperature difference. Now the Seebeck coefficient itself is temperature dependent. Therefore, if you wanted to calculate the voltage based on a temperature gradient, you would have to evaluate this integral over the Seebeck coefficient in dt. So how can we put the Seebeck effect to use? We just saw that if we heat up one end of a piece of material, then we get a voltage across it. Now, if we want to measure this voltage with a voltmeter, we need to make connections to the material. And these connections, of course, they also get hot, right? So we get a competing Seebeck voltage in these wires that connect to the voltmeter. If these wires are made from the same material, like the original piece of material that we were looking at, then the two Seebeck voltages will compensate and we will get a total voltage of 0 inside the voltmeter. The trick here is to make this junction with a different material. So let's say this here is aluminum, then we could use nickel wires to connect to the voltmeter, and because the Seebeck coefficient of nickel is different from the Seebeck coefficient of aluminum, we would get a different voltage in the aluminum than in the nickel, and so we could measure some voltage here on the voltmeter, which would be the difference between these two voltages. So a circuit like this here is called a thermocouple, and that's widely used for measuring temperatures. The voltage that you can measure in the voltmeter for such a thermocouple is governed by the difference between the two Seebeck coefficients. And so one can define a Seebeck coefficient between the two materials, SAB, that tells you essentially how powerful that thermocouple combination is in terms of generating a voltage depending on a temperature gradient. Here in this graph you see the Seebeck coefficients for a few popular thermocouple materials depending on the temperature. For one, you realize that they actually vary quite a bit with the temperature, but we also see that we have materials with some pretty big differences. So one popular combination is alumel and chromel, which is the type K thermocouple. And the type K thermocouple has a 40 microvolts per Kelvin Seebeck coefficient. So that's the SAB coefficient between these two materials. It is important to realize that thermocouple measurements are always the measurement of a temperature difference, right? If you look at the integral, we always integrate from temperature cold to temperature hot. So we only get a voltage that is depending on the difference between these two temperatures. Now, how do we measure an absolute temperature? Well, for that we need to create a temperature reference that we know, and a very popular one is to use ice water. Right, if you put ice cubes into a bucket and let it melt, you have exactly 0 degrees centigrade in that water bucket until all the ice is melted. So if we put one of the two thermocouple junctions into the ice water and the other one at the location where we want to measure the temperature, then on the voltmeter we get a voltage that we can evaluate in terms of absolute temperature here at the measurement point. It's interesting to note that when you buy a multimeter that has a thermocouple input, there the calibration is usually done with a calibrated analog integrated circuit that's inside the multimeter and measures the ambient temperature. The final point I want to make in chapter 4 is thermionic emission and vacuum tube devices. So here we ask the question, how can we get electrons emitted into the vacuum from a metal surface using heat? And I guess you know that by now. If we heat that metal high enough, then we will get enough electrons that have energy to overcome the work function between the Fermi level and the vacuum. If you consider an experimental setup like this here, so we have a vacuum tube, 2 electrodes, we can apply a voltage between the 2 electrodes, and then below the cathode here we have a filament with which we can heat it to a warm red glow. And at that point then, if we apply a voltage here that attracts electrons to the anode, we will measure a current. And similar to the photo effect, depending on the voltage that we apply, if the voltage is high enough, we collect all the electrons and then the current will saturate. The emitted current density is governed by the Richard-Dushman equation, which is essentially multiplying a constant with the temperature squared and then with the usual exponential function that compares the work function with the thermal energy of the electrons. It's obvious that either lowering the work function or increasing the temperature will make this current density bigger. Let's try to get a feel for how the work function and the temperature influence the current density. You know by now that when the temperature goes up, the Fermi-Dirac function gets flatter, and that means we get more electrons that have a higher energy. So that certainly helps to get the current up. Another way to get more current out of such an electrode is by lowering the work function, because that allows us accessing electrons with a lower energy for the current. So I did a calculation here to illustrate a little bit at what magnitudes the effects are when we turn those two knobs. So I assumed a tungsten electrode that's heated, and it has a work function of 4.5 electron volts. And so I calculated it for room temperature, and at room temperature you get an astounding 2.18 times 10 to the minus 76 for that exponential factor. So that means the current that is coming out of this electrode is absolutely negligible. So if we heat that electrode up to 1000 Kelvin, and 1000 Kelvin you can imagine is about red glowing, a little bit like one of those old-fashioned stovetop heaters when you forget to put a pot on it and it gets glowing red, then it has about this temperature. And so we see already that we get many magnitudes improvement. So now it's 2 times 10 to the minus 23. Certainly a big improvement, but we can gain another 10 magnitudes if we also reduce the work function. A popular material for coating tungsten electrodes is lanthanum hexaboride, LAB6, which has a small work function of only 2.6 electron volts. And if I do the calculation again for 1000 Kelvin and this low work function material, we get now 7.7 times 10 to the minus 14. So if you compare it to the minus 76 here, so we have more than 60 magnitudes different, which is very substantial. Another thing we can do to encourage electrons to leave an electrode is to apply a strong electrical field to it, and this is called the Schottky effect. The Schottky effect is often used in electron microscopes where it's important to get a strong electron beam, a high current electron beam. And so here you see a typical setup of an electron gun in such a microscope. You have a tungsten filament that's coated with LAB6, and that has a fine tip that enhances the electrical field. And then there is an electron lens, it's called a Wenel cylinder, and after that electron lens is the anode, which is used to apply this field to extract the electrons, the Schottky field. This here shows what happens when we apply that field in front of the electrode. Because of the field gradient, the Coulomb potential that prevents the electrons from leaving, that causes the work function, gets bent down here, and that creates an apparent work function lowering, which is similar to what happens when we simply coat the electrode with a low work function material. So this here gives us an additional work function lowering because of this field gradient in front of the electrode, and that increases the current. So the current density is governed by this equation. It's very similar to the Richard-Dushman equation, except that we get this additional term in the numerator under the exponential function, which allows us to calculate an effective work function. So this term that reduces the original work function is a constant, the Schottky coefficient multiplied with the square root of the electrical field. Unfortunately, the Schottky coefficient is rather small, right? It's 3 times 7, 9 times 10 to the minus 5. And that means that we have to apply some pretty strong fields in order to get a noticeable work function reduction. I did a quick calculation to see what field one would need to get a 1 electron volt reduction of the work function. And so if we solve this for the electrical field strength, and plug in 1 as the delta work function, then we see here that the field would have to be 7 times 10 to the 8 volt per meter. So this is a pretty strong field, and this explains why these electrodes are typically point-shaped and the distance between the anode and the electrode is relatively small. If we're still not satisfied with the work function reduction using the Schottky effect, then we can do one more thing. We can use a really high voltage that we apply in front of the emitting cathode. And when we do that, then the field gets so strong that the barrier gets so narrow that we start getting the tunneling phenomenon. So electrons that are close to the Fermi energy can already directly leave by tunneling through that narrow barrier that we generate with a very high extraction potential. So we get what we saw in chapter 3, that the electrons come from the inside of the metal of the tip to the surface, and then they find that potential, that narrow potential generated by the high extraction potential, and then their wave function exponentially decays through the barrier, and we get a sizable probability that the electrons can then leave the cathode. This process, which is called field emission, yields a strong increase in the current density because we start out with a large reservoir of electrons close to the Fermi energy instead of relying on the upper end of the Fermi-Dirac distribution like in the Schottky effect. The current density of this process is calculated with the Fowler-Nordheim equation, and in that equation we multiply a constant that contains the work function with the electrical field squared, and then in the exponential function here we compare essentially a term that contains the work function with the applied electrical field. And so the stronger the field, the stronger the emitted current density. Since we need such a large field to get this tunneling effect in the field emission process, the cathodes need to be very pointed to increase the field strength. And here you see a scanning electron microscopy image of such a tip. These tips are typically made by chemical etching, and one can make them as sharp as just having a single atom here at the end. This concludes chapter 4. Thanks for watching.